And we don't want to spend too much what are called Sankey diagrams, but a couple of things that come out of the study. So now we're starting to, we've run the study, we've pushed enter, and we're starting to look at some of the outputs here. Some significant differences you would see, I think, in what an African or a South African model would look like. This is US energy flows in 2015 and 2050. First thing I think that hits the eye is that even in 2050 in the US, a very small amount of solar, wind, and hydro. When I say small amount, anything that's small in America times the size of America is still a big number, but percentage-wise, it's still quite a small, thin line on the bottom graph. I think, and I would hope, in a South African study, those numbers, especially in 2050, would be percentage-wise a lot thicker. What you also see in 2050 in the US, and it's no surprise, is quite a large use of natural gas. The study assumes a $4 per million BTU price of gas over the lifetime of the study, which the Americans seem to think is a reasonable number. So natural gas figures very strongly in a US study. It may figure less strongly in a regional study in Southern Africa. And I know you had a talk yesterday on the prospects of gas. Unfortunately, I wasn't here. But gas features strongly in some of the work that's been put forward in IRP planning and things. So we also need to figure out what percentage gas would play in our studies. And then look at transport, which I think comes out very strongly. Not only is the dark brown, I think it comes out kind of like an ochre color. Not only is it much reduced in the bottom graph in terms of a percentage of liquid fuels, that's petroleum, that ochre color, but also the whole transport line is thinner. I don't know if you can notice that. These are obviously very poor diagrams, but it means less energy is being used for transport in 2050, less total energy than is being used on transport today in the US. And that's quite a surprise. And percentage-wise, less petrol or petroleum is being used even of that reduced line. So quite significant reduction in transport. What you might also notice is that the buildings line and the industry lines don't actually even get much wider. You don't see a lot of growth there. I'm going to touch on that shortly. So I mentioned those three pillars: transport, buildings, and industry. This is a US study. I keep repeating. At the moment, the percentage of final energy in the US, transport takes up 44% of it. Buildings take 30% and industry takes 26%. So by far the biggest use of energy in the US at the moment is transport. Final use. This is not electricity, this is energy. So now if you look at this, at the bottom line, 90... This is today. So this is establishing the potential. So this was like going into the study, what is the potential for energy efficiency? What is the potential for energy saving? And if we just stick with transport, but the same sort of logic applies to all of them, 96% of final energy is provided by fossil fuel in transport in the US today. So transport makes up 44% of the final energy use, and 96% of that energy comes from fossil fuels in the US. Now we can do a similar study, like I say, for any region in the world. Buildings, also interesting, 56% of energy comes from a fossil source in buildings. Now remember, in the US they use a lot of oil heaters and gas heaters, so those are fossil fuels that are used in buildings. I think that number in Southern Africa would be a lot lower. Although if you add biomass to the solution, because on a small scale in rural areas, biomass is your primary heating and cooking source, and that is we can argue whether it's a renewable or a fossil, but it's definitely carbon-based. And those figures might be high in certain rural areas of South Africa for building use. Right, so the areas of the sort of the sweet spots that came out of the study, so those long brown lines are petroleum-based fuels in use in cars and light trucks, heavy-duty trucks, aviation, bus, transit, rail, etc. So in transport at the top, buildings in the middle, and industry at the bottom. So now this all starts to come out of the data. If you haven't gathered your data sufficiently, you wouldn't be able to draw little graphs like this. But when you start to look at that and you see the breakdown between electricity, natural gas, petroleum, coal, and bioenergy, I mean, it immediately jumps out to you. And I said earlier that, you know, the majority of energy for transport comes from petroleum, and you can see that in all the brown bars at the top. So whether you're driving a light vehicle or you're flying an aeroplane or you're in the military, you're using petroleum. Whereas in the middle, you start to see a lot more use of electricity, the blue stuff, and also in industry and in agriculture. So when people look at saying, how do we mitigate greenhouse gas? How do we use our fossil fuels more intelligently? You need these kinds of bar graphs to say, well, where are we using our stuff? Where are we using all of our fossil fuels? The US National Energy Assessment had 4, just like our IRP had various scenarios. It had 4 scenarios, or does have 4 scenarios. It has a reference, it has a conservative, a progressive, and a transformative. Guys, all of this stuff is much more detailed in the report, which I gave you the link to, and you can spend the next few days reading. But these are the 4 scenarios that the model uses. And then for each of those scenarios, it makes some estimates. EPRI'S is the company I work for. ANL is Argonne National Laboratory. So ANL is Argonne. They make estimates about light vehicle use. The AEO is the US published annual energy outlook. It's a bit like the IEA outlook, but it's a US focused annual energy outlook. They look at economic growth and things like that. So you can get all of these estimates from various sources, and those were pumped into the reference case. Interestingly, the conservative case kept all of those except a slower decline in battery costs. So it wasn't as optimistic about energy storage. And then the progressive, and we talked earlier, the question was asked about transformative and transformation. Those 2 scenarios bring in RPS, stands for Renewable Policy Standards, on a statewide level. I've included that acronym at the bottom. And it brings in carbon taxes. So in the progressive and transformative scenarios, they bring in renewable policies and carbon taxes to try and drive towards certain fuel mixes. Again, no real surprises if you know anything about the US. If you want to cast your, if you're really a transformative kind of person, you would go to the right-hand graph and go out to 2050, and a lot of gas. But interestingly, a lot of gas was CCS, carbon capture and storage. I know you've had a presentation, I think, on carbon capture and storage. What was mentioned in the climate mitigation flagship projects. I used to be a member of the carbon capture and storage team here in Johannesburg, and so that's a debate all on its own whether that would actually take place. And remember, the transformative graph has a large carbon tax built into it. So the carbon tax in the transformative case is $50 US a ton. That's a big tax. That's 600 Rand a ton. And at those levels, it drives carbon capture and storage because it becomes affordable. So that's what the model starts to push out. But other things that jump out at you is that coal use declines in all models. Okay? Nuclear doesn't necessarily grow in any of the models. It's kind of, you've got these assets, they've got an 80-year life, you kind of got to keep them until they kind of, by the way, it's my mom's 80th birthday today, so she would be upset if I called her a nuclear power station. But kind of when they get to 80, you can say you can retire now, Mom. And that's basically how the US views their nuclear capabilities. They're not keen on building new stuff, but they'll look after the stuff they've got. Whereas Europe, on the other hand, is decommissioning nuclear and saying we don't even want the stuff we've got. So some interesting transformation there. And of course, some good growth on if you go to the right-hand side again, on solar, wind, and rooftop PV. But again, those are with those state-driven renewables targets. And these graphs would look different for South Africa, Southern Africa, Africa. This is where I think it starts to get really interesting for me, because I think this is happening even in South Africa. We saw this in Eskom over the last few years, and I'm sure it's still happening. So let's cast your eye to that blue little block. I don't even know if you can read it. Sorry, I'll read it to you. It says, electricity's role in the energy system has grown steadily. Can you read it? From 3% in 1950. Some people in this room were probably alive in 1950. So in America, in 1950, only 3% of final energy came from electricity. And that's not so long ago. It's now at about 20 to 21% of final energy comes from it. So electricity is growing as a final use product. But what also strikes me is that they're predicting, well, the model is predicting, if you look at the top of the brown sort of bar, a gradual decline in total energy consumption in the US going to 2050. And that takes into account GDP growth and population growth. Now, obviously, population growth in the US is pretty flat, but there is a GDP growth built in there. And so the US is predicting that even if they were to keep their economy structured the same, they will be using less energy in 2050 than they are using now. And that's what the modeling is showing. So where does that come from? Well, the first bit of decline is from structural change. And people ask, another word for that is transformation, but not the BEE kind. Structural change, I think the best example we see of structural change in our modern society is carpooling, car sharing, Uber, mass transport. Everyone in America used to own 3 cars, V8s, pumping out a huge amount of CO2. Even the Americans are starting to say, hey man, we only need a small car, and if we don't need a car, we can catch a train or we can catch an Uber. You've probably had presentations on the future of electric transport and the future of transport, but some estimates say there will be 1/3 of the cars on the road if everyone shared a car than there are today. And the utilization of those cars goes through the roof. So carpooling, car sharing, etc. is an example of structural change. Another example of structural change they're seeing a lot of in the US is work from home. A lot of people, I work from home now, isn't that a wonderful thing? Another reason I left Eskom, now I can work from home. So I don't commute anymore. I mean, my mileage has gone from like 2,000-3,000 kilometers a month to about 400. I drop the kids at school and I pick them up and I do a bit of shopping. And so I'm using my car a lot less because of a structural change. I'm able to work from home. Other things they're seeing in the US, they're seeing a move towards warmer climates. Now that sounds a bit strange, but a lot of the energy used in the US is on cooling and heating. So I should say more of a move towards moderate climates. So if you look on the West Coast, where there's San Francisco and Los Angeles and California, it is extremely hot. So they use a lot of energy on cooling. And if you look on the East Coast, New York, Washington, Boston, it's extremely cold in winter, even up to Chicago. They use a lot of energy on heating. They're finding, and one of the fastest growing cities in America is where EPRI'S head office is in Charlotte, which is kind of in the middle of the country, more of a temperate climate, and a lot of companies are moving there, not necessarily from an energy perspective, just because of its comfort of living perspective, but the net effect of that is that they are using less energy. Their businesses are using less energy because they're not heating and cooling as much. So human migration is also driving structural change. So there's lots of examples of structural change, but it's a massive hit on the energy demand. The other big hit on the energy demand is efficiency improvements. Now, all of these lines, by the way, there's empirical data behind these lines. There's not just Barry drawing pretty pictures. So the model spews out data, but it's only as good as the data you put in, and that's part of it. But let's just look at the qualitative effects. Efficiency improvements. Now, we all know what those are, hopefully. I mentioned the big V8 car that used to get maybe 10 liters per 100 kilometers. You're now getting cars that are using 3 liters per 100 kilometers. And that's not even an electric car, that's a diesel car. That's efficiency. And so you use less energy to do the same amount of work. And factories and businesses and homes, I mean, all of us, one of the, I guess, unintended consequences of load shedding is we've all become a lot more energy aware and a lot more energy efficient. LED light bulbs give out the same amount of lumens for a fraction of the energy. That's energy efficiency. And like I said earlier, Eskom is seeing some of these things now. I mean, I don't necessarily think that all of the flatness in the Eskom demand or the national demand curve is as a result of a flat economy. I think there's a large amount of efficiency built into that as well that we just haven't measured. We don't necessarily have our finger on it. And then electrification is fuel switching. So that little bit at the bottom there is where people have said, well, we won't use diesel or oil, we'll use electricity. And because it's a more efficient conversion medium, it reduces consumption even more. An example of that, and I've got some slides sort of at the back you can have a look at, is space heating. I used to when I was a kid, and I'm sure we all, well, when I was a kid we used to have a coal fire in that lounge, and we used to burn coal to heat the lounge. And then we got clever and we had an electric heater. Now you have a gas heater if you're even more clever, and the latest thinking is you must have a heat pump space heater. Those heat pumps are far more efficient than the coal I used to burn back in the day. So electrification of heating and clever electrification is reducing demand even more.